Ultimate strength design. Ultimate strength design utilizes reserves of strength resulting from a more efficient distribution of stresses allowed by plastic strains in the concrete and reinforcing steel, and at times it indicates the working stress method to be very conservative. Load and resistance factor design, which is abbreviated as LRFD, is a scheme of designing steel structures and structural components which is different from the traditionally used allowable stress format. Ultimate strength for LRFD, we have loads increase depending on type of load. And for the factors, we have for dead load, which is 1.4, live load, which is 1.7, wind load, which is 1.3. And for the ultimate strength combination or factors, we have 1.4 dead load plus 1.7 live load. And for the strength reduced depending on type force, we have the factors or the resistance factors. For flexure, we have 0.90, shear 0.85, column, which is 0.7. And for mu, which is the maximum moment or the ultimate moment, which is equal or less than the factor times mn, which is the nominal flexure strength. And for the ultimate strength, mu or m sub u is equal or less than 0.90 m sub n. And for shear, we have the maximum shear, which is equal or less than 0.85 Vn, or V sub n is the nominal shear. And for Pu, equal or less than 0.70 P sub n, where Pu is the ultimate axial load and Pn is the nominal axial load. And for the strength measurement, for the compressive strength, we have Fc prime, which is concrete design compressive stress, 12-inch by 6-inch cylinder, and for 28 days moist cure, the ultimate failure strength. So this is the sample test or the testing for compressive strength. We can find the value for F sub C prime or the concrete design compressive stress. And for the tensile strength, we have F sub T prime or concrete design tensile stress. And the same, we have 28 days moist cure, the ultimate or the failure strength, split cylinder test, and at 10% to 20% of Fc prime. For failure modes, we have rho, which is the reinforcement ratio, is equal to A sub S is the steel area, the total area for steel, divided by base times D, or the depth of the beam. For no reinforcing, means it is brittle failure. And for the rho minimum, 200 over Fy, wherein Fy is the yield strength. And for the reinforcing, less than the balance, steel yields before concrete fails, and it is ductile failure. And for the rho maximum, we have 0.75 rho balance. And for reinforcing, it is equal to balance. The concrete fails just as steel yields. And the rho balance, the formula is 0.85 beta 1, which is beta 1 is the coefficient multiplied by the concrete design compressive stress divided by the yield strength or the yield stress, and multiplied by 87,000 divided by 87,000 plus Fy. Reinforcing greater than the balance, concrete fails before steel yields, and there's a sudden failure. Actual value for reinforcement concrete should be greater than the rho maximum. It means that there is a sudden death, or it will have a failure. It should be in between rho minimum and rho maximum, that you can use the rho value. For flexure equations, we have the beam, we have the base B, and the depth D, or the effective depth, and the centroid of the beam, which is from the centroid up to the top fiber of the beam, that's C, and we have the steel area, and for the actual stress we have 0.85 FC prime, and this is the value for C, and for the ACI equivalent stress is 0.85 FC prime, and for compressive force it is 0.85 FC prime AB, where A is equal to beta 1 times C, or the coefficient multiplied by the value C. And for tension, we have area for steel multiplied by yield stress, Fy, or C for equilibrium. C is equals to T, and it is 0.85 FC prime AB is equals to A sub S F sub Y. Solving for A, we can find the value for A, which is equivalent to A sub S F Y all over 0.85 FC prime B, and equate that to rho Fy times D divided by 0.85 FC prime. And for the value for rho reinforcement ratio, it is equivalent to steel area all over B times D. And for the nominal flexure strength, it is equivalent to T times open parenthesis D minus A over 2 close parenthesis, and it is equal to A sub S times F sub Y multiplied by D minus A over 2, wherein M sub U, which is the ultimate or the maximum moment from factored load, is equal to the resistance factor multiplied by nominal moment, and Mu is equals to resistance factor times AS Fy times D minus A over 2, or the formula for ultimate or the maximum moment, it is equivalent to resistance factor times A sub S times F sub Y times D multiplied by 1 minus 0.59 rho F sub Y all over Fc prime close parenthesis. So this will be the maximum moment formula. And for balance condition, from similar triangles at balance condition, Fy over Es, or E sub S, and for the ratio, C over the total effective depth D is equal to 0.003 all over 0.003 plus Fy over E sub S. And the formula for C, from the centroid up to the top fiber of the beam, it is 87,000 all over 87,000 plus F sub Y multiplied by D. Use equation for A, then we substitute C is equals to A all over beta 1, and A is equal to rho Fy D all over 0.85 Fc prime, and C based on A over beta 1, it is equivalent to rho Fy D all over 0.85 beta 1 Fc prime. So this will be the equation to find the value for C, and equate the expression for C, and we have the formula for rho balance, which is equivalent to 0.85 beta 1 times Fc prime all over F sub Y, then multiplied by open parenthesis 87,000 all over 87,000 plus F sub Y and close parenthesis. So this will be the formula for rho balance. And for rectangular beam analysis, we have the base and the depth, or the effective depth, and the value for C, and the total area for steel. We have section dimension should have B, height, the height of the beam, depth, and the span of the beam. And for the steel area, or A sub S, material properties should have the Fc prime value and F sub y, and for the required strength of beam or the moment is equal to m sub n, and for the required by load moment, which is m sub u, and for the load capacity. And to find the value for rho, which is the reinforcement ratio, is equals to a sub s all over b d, and we need to check the value for rho using the rho minimum equation and the rho maximum equation. And once the value for rho is in between minimum and maximum, you can use the value for rho. If the rho value is below the rho minimum, use the rho minimum, and when the value for rho is more than the rho maximum value, then you should redesign the size of the beam. And to find A, using the formula, and find m sub n, and then you calculate m sub u, which is equal or less than the value for the factor resistance factors times m sub n, and we can determine the maximum loading or the span. So these are the formulas to be used. Example: a reinforced concrete beam having a width of 12-inch and a height of 20 inches with effective depth of 17.5 inch is reinforced with 3 number 8 bars. Fc prime is equals to 4000 psi and Fy is equals to 60,000 psi. Compute the ultimate moment capacity of the beam and check for rho. So we have a beam, and the size of the beam, this is the base or the width, this is equivalent to B is equals to 12-inch, and the depth or the effective depth, and the D is equals to 17.5 inch, or the height is equivalent to 20 inch. With area of steel, we have 3 of number 8 bar, and we have PC prime, which is 4000 psi, and Fy, which is 60,000 psi. So we will compute the ultimate moment capacity, that's mu. So we have a question mark of mu, and check for rho. Rho minimum is less than rho and less than rho maximum. A number 8 bar is the size of a number 8 bar is equivalent to 25 mm diameter, or it is equivalent to 1 inch. And we will find the area or A sub S, or the total area for steel. We have 3 bars, and the area of number 8 bar, which is 1 inch, we have pi over 4 d squared, and the diameter of a number 8 bar is 1 inch, and multiplied by 1 squared, and this is equal to 2.37, and it is in inch squared. And we check for rho. Rho formula is equals to A sub S all over B D, where A sub S is equal to 2.37, and we divide by B, which is equivalent to 12 inch, and D, which is the effective depth, and it is 17.5. So rho actual is equivalent to 0.0113. Check for rho balance, and the formula for rho balance, it is 0.85 Fc prime beta 1 all over Fy, and multiplied by 87,000 all over 87,000 plus Fy, and 0.85 times Fc prime, which is equivalent to 4,000, and beta 1, the constant or the factor for beta 1, it is 0.85, and we divide for Fy, which is 60,000, and multiply by 87,000 all over 87,000 plus 60,000, and by computation, row balance 0.85 times 4,000 divided by 0.85 over 60,000, so we cancel out 3 zeros, and multiplied by 87,000 all over 87,000 plus 60,000, and the value for row balance, that's 0.0285. So we have now the row value, which is equivalent to 0.0113. Row balance is equal to 0.0285, and we check for row maximum, and the formula for row maximum, that's 0.75 of row balance, and this is 0.75 times 0.0285, and row maximum, it is equivalent to 0.0214. So row maximum, that's 0.0214, and we find for row minimum, and the formula for row minimum, that's 200 all over Fy, and we have 200 all over F sub I, or F sub Y is 60,000, and we have row minimum, that's equivalent to 0.0033, 0.0033 for row minimum, and we check for row minimum is less than row actual and less than row maximum. So row minimum is 0.0033, less than row actual, that's 0.0113, and less than row maximum, that's 0.0214, and this is okay. Next, after we check for row, we will find now the value for A, and the formula for A, we have A sub S times Fy all over 0.85 Fc prime times B, and then we substitute the value for A sub S, total area for steel, that's 2.37, and Fy 60, and Fy 60,000, and we divide by 0.85 multiplied by Fc prime, that's 4,000, and multiplied by B, that's 12 inch, and A is equivalent to 3.49 inch. And next, we find the nominal moment M sub n. M sub n, or the nominal moment, we have the formula As times Fy times D minus A over 2. And area for steel, that's 2.37 multiplied by F sub Y, that's 60,000, and D, we have the effective depth, that's 17.5, less A, which is 3.49, and we divide by 2, and we have nominal moment m sub n, and it is equal to 2,240,361, and that's pound inch. M sub u is equal to coefficient multiplied by m sub n, and we have the coefficient, the value is 0.9, and m sub n, that's 2,240,361, and the value for m sub u, or the ultimate moment capacity of the beam, it is equivalent to 2,017,000, and it is pounds inch, and we convert that to kips foot, so we divide by 1000 to make that kips, and inch converted into foot, that's we divide by 12, so 1 foot is equals to 12 inch, or it is equivalent to 168 kips foot, and this is the value for ultimate moment capacity.